Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. We have finally come to the place where we have our board complete. We're ready to test our first prototype. Brace yourself though, as with any first prototype, this is where we discover things like design and assembly flaws. While I have had many pleasant experiences over the years of things working perfectly right out of the gate, I've also had those times where something was put together wrong or there was an unanticipated reality that required a change in design. So we must remain objective and anticipate that it just isn't going to be perfect right out of the gate. Remember, this is prototype number 1. I've also seen where prototype number 1 worked just fine. Then we built 4 more prototypes and, well, prototype number 5 had an issue relating to a part on that board being at the other end of its tolerances from the rest, rendering the board unacceptable. We had to make changes to accommodate the entire tolerances of all of the parts included in the design, and then we were golden. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, I have the board on the bench. Let's see what reality is. Initial testing begins with what I call smoke testing. This is where I apply power to the board and watch for the magic smoke being released from some component. It is also where I quickly check to see if the power supply is giving us the voltage we want. What are our expectations? Well, according to the data sheet, the positive supply should be within 3% of nominal and the negative supply within 5% of nominal. For the positive supply, it can be from 8.73 volts to 9.27 volts. For the negative supply, that can be between 8.55 volts and 9.45 volts. Okay, so let's see how we're doing. Let's connect the 12-volt DC regulated wall wart. Woohoo! No magic smoke! No smell of burning tires! Check! First observation. The blue power LED is so bright it just about burns out the retina. I think we could double the value of the current limiting resistor to tone down this a bit. But this is kind of a forewarning that the other LEDs are going to be very bright too. All right, let's see what the power supply voltage is. I can measure it across these capacitors right here. All right, here we go. And here. 9.01. and 8.95, well within the tolerances of the CUI power supply module. So now let's move on to the next test, the basic functionality of the analog chain. When I talk about the basic functionality of the analog chain, I mean that I'm going to apply a signal to the input channel, look at the output of the mixer, and observe that the appropriate LED illuminates on cue. I'm not going to be measuring gain or frequency response or the exact dBu level that the LEDs illuminate at. I just want to see if things are doing something that approximates what they're supposed to do. What I'm looking for are the gross errors. I will be testing with an audio frequency of 1 kilohertz. At a level of 50 millivolts peak to peak from my signal generator. I will apply this to channel 1 input. I will observe the mixer output using my oscilloscope. I will vary the various level controls to observe the output voltage and the action of the LEDs. So let's go to the bench and see how we fare. Analog output first. All right, so let's turn up the channel a little bit. We don't see anything on the output yet because the output control is not all the way up. And we turn that up and we see a very nice clean sine wave there. I have no complaints about this. That looks really good. All right. Now, let's change our signal generator to 150 millivolts, peak to peak. We should certainly be able to get our peak LEDs to light up that way. And I'm not seeing anything going on there. All right, that's not good. Let's go to the next channel, channel 2. And that LED is not doing anything. Channel 3. And that LED doesn't seem to be doing anything. We are seeing an output on the scope for channel 3. We are certainly seeing an output on the scope for channel 3 there. Notice too that these LEDs are, at least the 3 middle ones are, the lowest one isn't. So that makes us ask the question, what is going on? Why are these 3 LEDs and this one not lighting up at all? So this will be on the indicators page. This is the input amplifiers here. So let's go to the indicators page. And if we take a look here, we have channel 1 peak detector is U41, and channel 2 peak detector is U41, the second section, and channel 3 peak detector is U41, the third section. And then over here we have the minus 30 dBm LED uses the fourth section of U41. So goodness, this looks like all of these LEDs have U41 in common. So it's time now to take a look at the board itself and find out what's going on. Now I'm going to take a quick look at U41 on the board. Do you notice anything wrong with it? Well, notice this little white dot right here. This white dot indicates that this is supposed to be pin 1 of the chip. Notice this line on the chip here. This is the pin 1 end of the chip, which means the chip pin 1 is here. The board wants pin 1 here. This thing has been mounted 180 degrees out of what it should be. Well, there are no guarantees that this chip is any good at this point. Who knows what damage having it mounted wrong and the power supplies connected up wrong and all that did to it. The only solution is to replace this chip entirely. Now, I'm really glad that I ordered extra chips. Like I said, stuff happens. Did you know that you had mounted U41 on backwards? What? Oops. Okay, now that I've replaced the chip, let's see how it works. Well, power comes up. That's a good sign. No magic smoke from anywhere. That's a good sign. I am inputting 150 millivolts peak to peak to channel 1. And I'm doing that so that I can make sure that my peak LED lights up. So to begin with, everything's turned down. And now we turn up this, channel 1, and we can see that the peak LED comes on. That's good. I'm going to switch over to channel 2. Make sure its peak LED comes on. It comes on, that's good. Switch over to channel 3. Make sure its peak LED comes on. It comes on. So we'll turn that down a little bit. Now we want to see if these are going to operate. So we'll turn this up and we get the minus 30 and the minus 20 and the minus 10 and the minus 3 and the plus 3. All right. So everything is operating as it should. Now comes the time when we're going to look at the frequency response of the overall thing, the overall gain, and we're going to look at the signal level that each of these LEDs turn on at. That's our next step. To test the overall gain, I needed to make sure that I had a nice, clean, low voltage input signal. To ensure that I had that, I created a 100 to 1 voltage divider using a 100 ohm surface mount resistor soldered across the input connector and a 10 k ohm resistor in series with the signal generator signal. I measured the actual resistance of each of the resistors using my DVM and calculated the actual voltage gain of the divider. It turned out to be 101.1 to 1. Now I set my signal generator to 1 volt peak to peak at 1 kilohertz. I measured the actual output voltage of my signal generator using my oscilloscope at 0.992 volts peak to peak. So all of this gives me about 9.81 millivolts peak to peak as the input to my mixer. Now I measure the output voltage of the mixer with the gain controls turned all the way up. Now we need to ask, well, what is our target gain? We have to know what we're shooting for after all. Well, the design calls for the input amplifiers to have a gain of 100 or 40 dB, and the output amplifiers to have an additional gain of 3.16 or 10 dB. So our overall gain should be somewhere on the order of 316 or 50 dB. So let's see what we got. Well, the output voltage with our input connected to channel 1 is 3.09 volts peak to peak. Now, with 9.81 millivolts on the input and 3.09 volts on the output, this gives us an overall gain of 314.9, which is within 0.5% of our target. With the input connected to channel 2, the output voltage was 3.08 volts peak to peak, which gives us a gain of 313.9 or 49.9 dB, and this is within 0.7% of our target. And then finally, the output voltage with our input connected to channel 3 is 3.09 volts, just like channel 1, so 314.9 is the gain within 0.5% of our target. So that is like way perfect. Now, let's turn our attention to the actual signal levels that the LEDs illuminate at. So, let's start with the peak indicators. According to our initial design, the peak indicators should illuminate at plus 6 dBu, and we calculated this to be 2.185 volts peak or 4.37 volts peak to peak. This has to be present at the output of the input amplifiers. So what do? I set the input signal to achieve 50 millivolts peak to peak so I can be sure to illuminate my LED. Then I increase the channel level pot until the LED just illuminates. and then I measure the amplitude of the signal at the output of the channel input amplifier. The actual voltage is 4.06 volts for channel 1. If we back calculate this to our dBu value, we're looking at 5.36 dBu. Now, considering the purpose of the peak LED and the fact that, well, marketing didn't give us any tolerances on this, this is quite sufficient. I checked each of the other channels and I got the same results. Okay, now the output level indicators. This one is adjustable. So we begin by setting the signal level for -3 dBu on the output, and then adjusting the tiny little pot to make the LED just light. The -3 dBu LED should illuminate at 0.584 volts RMS, which is the same as 1.652 volts peak to peak at the output of the mixer. Now, with that done, let's check the levels of the LEDs. Starting with the -30 dBu LED, it illuminates at -31.5 dBu. The -20 dBu LED illuminates at -21.7 dBu. The -10 dBu LED lights at -10.2 dBu. And we have the -3 dBu lighting up at -3.2 dBu. And then finally, the +3 dBu LED illuminates at +2.99 dBu. These are all well within reasonable tolerances of their target values, especially when we consider that they're not a measurement instrument. They are intended to give the operator an idea of what the signal level actually is. I call this a victorious pass. Now, on to the last set of tests, the frequency response tests. All right, I am ready to do the frequency response test. We have the inputs and outputs set up on the back, and this is all connected up to my Velman USB oscilloscope, which also has a signal generator on it, and it will do Bode plots for me. Let's see how it looks. Having run the frequency response tests and exported the data to Excel, let's take a look at how we did. As you can see here, the responses from 20 Hz to 20 kHz are all within the -3 dB limits originally designed. And so I thought I was all done with the testing. I was feeling really good about the whole thing, until I saw this out of the corner of my eye. Notice the output level meter LEDs that are lit. And I don't have anything connected to the input. These levels are turned all the way down. This is turned all the way up. And if I turn it down, they go away. If I turn it up, it goes up. The First thought is that this is because of oscillation going on, and the level meter is showing the level of the oscillation. Let's see if that's the case. So I connected the oscilloscope up to it. If it were oscillation, we should be able to see that on the trace on the oscilloscope. And, well, it is absolutely clean. What changes when I change the setting on the level control? Well, that's interesting. I just turned it down and I turned it up. Well, this is capacitively coupled. I'm wondering if the DC level of the output of the amplifier is changing with the volume control. So I've connected my scope up to the amplifier side of that output capacitor, and I'm going to turn up the level control. Ah, looky there. So it is a DC thing. Well, going back to the schematic, this is all DC coupled all the way through. And so we were seeing a change in DC level. Here. And if we notice that that is also where 2 level meter goes. So let's go down to the level meter. And we can see that this is also DC coupled, as is all of the level meters. But it's a specific problem with this one because this level meter is measuring minus 30 dBm and minus 20 dBm. So we can fix this by putting a capacitor in here. And I'm just going to pick a 1 microfarad capacitor, I believe, that I'm going to put in series with this R64, this 82K resistor. All right, so let's give that a try. Where are we going to put it? So let's take a look at the PC board. Our R64 is right here. And we have the trace here. If we back out, we can see the trace up here. So we could put the capacitor in here. But notice I have this long line on the bottom side of the board, which would be also a place to put it. Might be a little easier. And if you notice, we have all this extra room here. So I think I'm going to cut the trace in here and solder my series capacitor right across here. So this looks like it's the trace that we're interested in right here. And so I'm going to cut the trace here, scrape off the solder mask, and install my capacitor right there. And there. With my pot all the way up, they're all off. And with my pot, see, look at that. I turn it all the way down, and I turn it all the way back up again. Okay, so the LEDs behave now, but I have to go back and recheck the LED levels. And here are the results. Minus 30 dBu illuminates at minus 32.19 dBu. Minus 20 dBu LED comes on at minus 20.74 dBu. Minus 10 dBu LED illuminates at minus 10.2 dBu. The minus 3 dBu LED lights at minus 3.2 dBu. And finally, the plus 3 dBu LED illuminates at plus 2.99 dBu. So we are good to go. Well, the first prototype of this mixer has passed all of its tests, well, with a few modifications. If you're wondering how it all looks in its enclosure, well, here it is. So there is the mixer. I have it connected to a microphone at the moment. So I have all my labels on it. It's in the enclosure. And if I get up closer to the microphone, you can see that it is responding as it should. So there you go. If this were a real product to be shipped to customers, whatever changes we made in the design with this prototype would be folded into a new version of the schematic, a new version of the PC board, and the bill of materials. We would not want any rework to have to be done on the boards when they're being made. This gets expensive and cost of goods goes up dramatically. However, this customer is happy with it just like it is. If you found this video helpful, please click on the like and subscribe to this channel. Thank you so much for watching. Until next time, Toodle-Oots.